In this final video, I want to do 3 last misconception questions, and then I want to look at our finale of why do we care? That's involving neurons and how charges flow across neurons. So first misconception question, here it is. Which way do electric field lines point? From high to low potential or from low to high potential? All right, well, let's just take a look at a proton. We have a proton here. We know electric field lines point away from them, right? And we know that the electric potential is V equals KQ over R. All right, so you have these equal potential lines that the smaller R is, the bigger they are. So this would be like 100 volts to 50 volts to 10 volts out here, right? So it would appear, just from looking at how this works, that electric field lines point from high potential, 100, down to low potential, 10 in this case. So easy breezy. Electric field lines point from high to low potential. Misconception question number 3. The potential difference between the 2 terminals of a AA battery, so here let's look at a AA battery again. And we have this kind of 0 volt side, the negative side, and we have the 1.5 volt side, the positive side. So that the delta V is equal to 1.5 volts. If 2 AA batteries are placed end to end, with the positive terminal of one battery touching the negative terminal of the other, what is the potential difference between the terminals at the exposed ends of the combination? So this is saying, let's add another one, like this, which, anything that you use that says, 2 AA batteries or 3 or 4 AA batteries, that's what's happening. You're adding them in series to each other, right? So if this difference is 1.5, and this difference here is 1.5, then the difference between the whole thing, very simple, must be delta V equals 3. You just add them up, right? Just because you're connecting them doesn't mean the difference goes away. The difference is going to add. So the more of these you add together, you could add 4 of them together, and you will get 6 volts, and on and on and on. All right, misconception question number 3 is over. Misconception question 4. It is easy to produce a potential difference of several thousand volts between your body and the floor by scuffing your shoes across a nylon carpet. We've all seen that. We know why that happens. You accumulate these charges, and those charges want to jump off to another object, and you will shock something, or something will feel, the electrons will actually jump to you. So yet, the contact with a power line of comparable voltage would be fatal. Why is there a difference? So this is a good question. So if I can develop about the same charge, or the same potential difference between me and a doorknob as what you experience in a power line, which is really only 120 volts, why is it that the power line could possibly be fatal if it shocks you? And so the answer to this question is going to be more clear next week when we start talking about current. But it turns out that it's really not potential that is harmful when you're getting, zapped. It is actually the current, which is the number of charges per second, right? It's the flow of charge, how many charges. Now, there is a direct relationship between potential and current, but if something has a high resistance like our bodies, the current's going to be a little bit smaller than it would be if there's something like a low resistance, like power lines that are conductors designed to have really low resistance. That'll create a very, very high current. High current means more electrons are zapping you, and more electrons means more energy that can hurt, cook, burn, electrocute you. All right? Hope that makes sense. So the power lines may have the same voltage that you can accumulate, but they have much higher current, and that current is really, really what does the damage when you're electrocuted.